Today we will calculate the packing efficiency in body-centered cubic structure. Packing efficiency is defined as the percentage of total space occupied by the particles that is atoms, molecules or ions which are packed together in a solid. Packing efficiency can be calculated as volume occupied by the spheres in the unit cell divided by total volume of the unit cell multiplied by 100. Let us calculate the packing efficiency. Here in this type of unit cell, that is BCC, we can see that the spheres which are placed along the corners of the unit cell do not touch each other. Here the spheres are placed at the corner of the unit cell, as well as one extra sphere will be placed at the body centered position. We can see from this unit cell also. Here the atoms are placed at the corners of the unit cell, as well as one extra atom will be placed at the body centered position. Now the spheres which are placed along the body diagonal, it is a sphere which is placed at the body centered position. Spheres which are placed along the body diagonal touch each other. Spheres which are placed along the body diagonal touch each other in this type of unit cell. Now let us these three spheres 1, 2, 3 which are placed along the body diagonal, their surface touch each other in this type of unit cell. Let us calculate or study the packing efficiency with the help of this diagram. Now in this figure, AB represents the edge length A, BC is also equal to A and CD is also equal to A. This is a cubic unit cell, and that is why all the three edge lengths are equal to each other, and all the three angles alpha, beta and gamma, they are also equal to each other, and they are also equal to 90 degree. Now let us consider the triangle ABC. A, B and C. This is a right angle triangle, and according to the Pythagoras theorem, this AC square will be equal to AB square and BC square. AB is equal to A, and BC is also equal to A. So substituting the value of AB square and BC square, AC square will be equal to A square plus A square, and that is equal to 2 twice of A square. In this triangle, AC square is equal to 2A square. Now let us consider this triangle A, C and D. This is also a right angle triangle. Here this AC, that is the face diagonal, is drawn over the plane of the paper, and this is perpendicular over this plane. So the angle ACD will be equal to 90 degree. This angle is also equal to 90 degree. So this longer triangle, this larger triangle ACD is also a right angle triangle, and AD is a hypotenuse. So in this triangle, AD square will be equal to AC square plus CD square. We have calculated AC square as 2A square. Now in triangle ACD, AD square is equal to AC square plus CD square, and AC square is equal to 2A square and CD square is equal to A square. So AD square is equal to 2A square plus A square, that is 3A square. In this unit cell, the spheres along the diagonal touch each other. We can see that the spheres along the diagonal, that is body diagonal, touch each other, and therefore this diagonal is made up of 4R. This is equal to 4R, R plus R plus R and plus R. It means 4R is equal to AD. Now we have calculated as AD square is equal to 3A square, or taking the root on both the side, AD will be equal to root 3A. Now equating these two, we get 4R is equal to root 3A, or R is equal to under root 3 by 4a, or a is equal to 4r upon root 3. Now this is the formula where we will substitute a in terms of r. A is equal to 4r divided by root 3. Now let us calculate the volume of the unit cell. Volume of the unit cell, that is cubic unit cell, is equal to a cube. And if we substitute a in terms of r, which is equal to 4r upon root 3, volume of the unit cell will be equal to 4r upon root 3 whole raised to the power 3. That is, a cube is equal to 4 by root 3r whole cube. Now let us calculate the number of atoms per unit cell in BCC. We know that the atoms are placed in case of BCC, atoms or spheres are placed at the corner of the unit cell, as well as one extra sphere is placed at the body center position, and the corner contributes only 1/8 part. So the total number of corner is 8. 8 multiplied by 1 by 8. So contribution from the corner comes out to be 1, and one atom is isolated to this unit cell only because it is placed at the body center position. So 1 plus 1, 1 contributed from the corner and 1 from the body center position. The total number of atoms per unit cell in BCC comes out to be 2. So there are 2 atoms per unit cell in BCC. So the volume occupied by the 2 spheres in this unit cell will be equal to 2 multiplied by 4 by 3 pi r cube, where the volume of the sphere is equated as 4 by 3 pi r cube, where the r represents the radius of the sphere. So the total volume occupied by the spheres in this unit cell is equal to 2 multiplied. There are 2 atoms, so 2 multiplied by the volume of the sphere, that is 4 by 3 pi r cube. The volume occupied by the sphere will be 2 multiplied by 4 by 3 pi r cube. Now let us calculate the packing efficiency. Packing efficiency is calculated as volume occupied by the 2 spheres present in this unit cell divided by the volume of the unit cell multiplied by 100. Now here the volume occupied by the spheres in the unit cell is equal to 2 multiplied by 4 by 3 pi r cube, and the volume of the unit cell is equal to 4 by root 3 r whole cube. This is 2 multiplied by 4 by 3 pi r cube is the volume occupied by the 2 spheres in the unit cell, and the volume occupied by the unit cell is equal to 4 by root 3 r whole cube multiplied by 100. This is equal to 2 multiplied by 4, that is 8 by 3 pi r cube multiplied by 100 divided by 4 cube is equal to 64 divided by root 3 multiplied by root 3 multiplied by root 3. Root 3 multiplied by root 3 will give you 3 multiplied by root 3, and on solving this we get 68% of packing efficiency. This packing efficiency is equal to 68%. In case of body centered cubic unit cell, the packing efficiency comes out to be 68%. So we have concluded that the packing efficiency is equal to 68%. Thank you.